Hi, this is Jay McClellan, and in this video I'm going to build a quadcopter or drone with a stabilized camera platform for shooting aerial video. And I'll build this using commonly available, fairly inexpensive components with a really simple design. So if you've never built a drone before, this will be a great place to start. And even if you have built a drone before, you may find some of this useful because in the first part, this part 1 video, I'm going to go through not only the component selection, but also optimization using some numerical modeling. So we'll use a numerical calculator to predict the performance of the drone with various components and use that to select the components that give us the best performance. In part 2, I will build the actual drone. So we'll build the flight section, the drive section of the drone, and with motors, propellers, batteries, and it'll be a fully functional quadcopter that we can go fly. But that's it. That's the end of part 2. And then in part 3, I'm going to build a detachable modular payload section. The first payload section I'm going to make is going to be the stabilized camera platform, but I'm designing it with a modular disconnect so that I can build other payload sections in the future, and I can mix and match drive sections and payload sections. So let's get started. Here are all the parts I'm going to use to build my quadcopter, and really this is everything you need except for little stuff like screws and wires. I'll go through each of these in more detail individually after, but first I'll start with an overview of everything. On the left I have a frame kit with 4 legs and 2 plates that tie them together. In the center I have a battery to power everything. I have a radio receiver, and of course there's a transmitter that goes with that. I have a little power adapter to provide 5 volts that runs this flight controller. The flight controller is really the brains of everything. It's what keeps the quadcopter level, and it drives the motors, which are up here, through these electronic speed controllers. And of course we have 4 propellers, 2 left, 2 right. In the next segment I'll show you the specific components I'm going to be using, and I'll give you the make and model number of each one where it matters. None of these are paid endorsements. Nobody pays me to advertise their stuff, darn it. So this is just stuff I've bought, and generally if you find something from another maker with similar specifications, you'll probably get similar performance. Most of these components are pretty interchangeable from one manufacturer to the next. This is the frame that I plan to use. It's a cheap copy of a DJI Flamewheel F330 frame. This cheap copy though sells for about $16, and that includes the optional landing gear, so it's really affordable. And my advice is if you buy a frame like this, get 2 so you have replacement parts. You can also buy a quadcopter frame as part of a larger kit that includes all the other components bundled together, or you can just buy it separately like this, as I did. When you look at airframes, you'll see that they often have a number like 330 or 250 after the model, and that refers to the distance diagonally between motor centers. So this one is 330 millimeters from center to center at the longest distance between the motors. A very common size is 250, which is especially popular with racing quads. So this is a little bit bigger, but not by a lot. And I like this size for my purposes because a little bit larger airframe actually makes the motors a little more efficient, and I'll go into that later on. So a basic airframe is perfectly fine for getting started. It may not be as light as some of the higher end frames, and it may not be as strong, but it's cheap to replace, cheap to repair, so I think this is a good choice for a first quadcopter. I've also made some quadcopters using my 3D printer, and here's part of a test flight of one such frame I made with these 3D printed propeller guards you can see in the bottom of the frame. And this flight went along pretty well until one of the rear propeller cards broke. So I don't recommend 3D printing a frame for a first attempt at building a quadcopter. Here are the drive components you'll find on each arm of the quadcopter. You have a brushless DC motor, propeller, and an electronic speed controller. The brushless DC motor comes in different sizes, and later on I'll talk about how to pick the right size. But they're all kind of similar in size for a quadcopter in this size range. And the DC motor has 3 leads on it, and the speed controller has 3 leads that connect to the motor, and you can connect them in any order you want. The way most people do it is just hook up the 3 leads, try it out, and if the motor goes backwards, swap any 2 leads to change the direction. Done. The speed controller also has 2 leads that connect to the battery for the high current power supply, and then it has a signal wire that connects to the flight controller, and that's how the flight controller instructs each motor to run at a certain power level in order to balance the craft and to navigate the craft. A brushless DC motor has a rating such as this one, rated at 1900 kV. The kV rating of the motor determines the relationship between the motor's input supplied voltage and its speed. That's kind of a simplified explanation, but it's good enough for most purposes. 1900 kV essentially means 1900 RPM per volt of input. Again, that's a little bit simplified, but it's good enough for our purposes. What that means then is the bigger that number, the faster the motor is going to turn for a given voltage. And it works out that motors that spin faster tend to be most efficient with smaller propellers and better suited for smaller quadcopters. Motors that spin slower tend to be suited for larger propellers and better suited for larger quadcopters. So 1900 kV is a good size for the quadcopter I'm going to build, and again, I'll go through the selection of that in the optimization portion a little bit later on. So that's the main rating you need to look at in terms of motors. The other thing to know is that they come in clockwise and counterclockwise versions. That doesn't actually have anything to do with which way the motor spins. You can reverse its direction by swapping any two of its three input leads. Clockwise or counterclockwise simply refers to the threading on the nut if it has one. This particular one is a clockwise motor, so it has right-hand threads on the propeller nut. A counterclockwise motor has left-hand threads, so that when the motor spins, it tends to tighten the nut. Some of them have universal design where you can use the same motor in either direction and the nut is tightened in another way. But most of them are listed as right-hand or left-hand, or clockwise or counterclockwise, and you need two of each for a quadcopter. Hobby propellers, even in metric using parts of the world, are generally specified in terms of inches diameter, and they're specified in terms of inches of pitch. And a simple way to look at the pitch of a propeller is if you imagine it screwing its way through a semi-rigid medium like clay. As it rotates one complete revolution, it would move forward by a number of inches equal to its pitch. This particular propeller is an 8 by 3.8 propeller, which means it's 8 inches in diameter and it has a pitch of 3.8 inches. Those are the two main things you need to know to specify a propeller. And the third thing is whether it's right hand or left hand. They come in both flavors, and you can't just flip the propeller over and have it work the other way. It doesn't work like that. So for a quadcopter, you need two right hand propellers, two left hand propellers. The simplest way to understand which is which by looking at a propeller is if you imagine a fixed wing aircraft with a propeller like this. If you stand behind the aircraft and look at the propeller in a conventional, typical fixed-wing aircraft, look at which way the top of the propeller moves, and that's whether it's right-hand or left-hand. For each motor, you need an electronic speed controller, and the main thing to look at in electronic speed controllers is their continuous current rating. This particular one is rated at 18 amps continuous current. They'll also have a peak current rating that's quite a bit higher than that you can run for a short time without overheating them. We'll look at that a little bit later. The next thing to look at in a speed controller is its weight in grams. It's not a real critical parameter because even the larger ones don't weigh all that much, but this is a really lightweight type, so I like this particular one. And finally, you need to pay attention to the voltage rating of the speed controller. I'll talk about batteries in a moment, but that's usually given in terms of how many lithium polymer cells in series it will handle. That's how the voltage rating is specified. This particular one is rated at anywhere from 2 to 4, which will be, as I'll show you in a moment, a 2S to 4S battery rating. Those are the main things you need to know about speed controllers. You'll find some of them that have BEC, which is a battery eliminator circuit. And the battery eliminator circuit will take the higher voltage from the battery and provide a 5-volt output. I prefer not to use those. I have a separate little regulator that I use to get 5-volt output to drive the receiver and the flight controller. At this point, you may be wondering why we'd go to the trouble of picking all these components individually and hooking them together. And it's a great question when you can get commercially built drones ready to fly for almost no effort. And honestly, if you've never flown a drone before, by all means, go out and buy a cheap one like this. This is my first drone. First one I built, it's a Hubsan X4. They sell for about 50 bucks, so it's pretty hard to go wrong, and they're practically indestructible. I have flown this into buildings, I've flown it into trees, I've dropped it from high altitudes without power, and about the worst it's done is broken a propeller, which are cheap to replace. It's got a built-in camera for shooting video, so you can have a lot of fun with a little drone like this. But it's got some limitations. The video quality isn't great, and so I'd like to have something that can carry a better quality camera. I'd like to have the modularity to carry different types of cameras or other payloads, and so that gets me motivated to build my own drone where I can swap payload sections around. And I really want something with longer flight time. This has about 5 minutes of flight time, so you got 5 minutes to get up, shoot whatever video you're going to get, and bring it back down to land it safely before the batteries run out, and that's kind of tight sometimes. So to get longer flight time, you need a drone that can carry more fuel, and that brings us to the subject of batteries. These are examples of batteries that can be used in quadcopters, and as you can see, there's quite a range of sizes. So when you look at a battery pack, it's important to understand the numbers that are given in its specification and know what they mean so you can pick the right battery pack for your application. The first number to look at in a battery pack is its voltage, and often that's specified in terms of how many lithium polymer cells are connected in series. This unit is just a single lithium polymer cell with a nominal voltage of 3.7 volts. These two units each have 3 cells connected in series inside, and so that's often specified as 3S, and you'll see it on the label, often 3S. So with 3 cells in series, they have a nominal voltage of about 11.1 volts. This large battery has 4 cells connected in series internally and has a voltage of 14.8 volts. The next number to understand is the total capacity of the battery, and that's usually specified in milliamp hours. This large battery pack has a capacity listed as 1600 milliamp hours or 16 amp hours, meaning that it could go from a full charge to a complete discharge by delivering 16 amps for 1 hour. That doesn't tell you how much energy this will hold, though. You need to multiply that by the voltage to get the effective energy that this will hold in watt hours. The available energy in a large battery pack like this is approximately equal to the amount of energy released by detonating 1 stick of dynamite. So that sounds like a lot of energy, and it sounds very dangerous. Well, it is. You have to respect the amount of energy that is available in a large battery pack like this, and really any lithium polymer battery pack. However, dangerous as that might sound, it's also about the same amount of energy that you derive by digesting 2 bananas. Now that doesn't sound so dangerous, does it? The big difference, of course, is the rate at which the energy is released, and we call that power. So this battery pack can be fully discharged, can release all of its energy without any damage in about 6 minutes. And you can discharge it faster, but it may damage the battery. So if you discharge this battery in 6 minutes, it'll deliver a power of about 2,000 watts or 2 kilowatts. The dynamite releases all of its energy in about 3 microseconds. And by releasing that same amount of energy in 3 microseconds, its power is about 200 gigawatts. That's about 100 times as much power as an average nuclear power plant produces. So that's a really high rate of energy release, which is why dynamite can be very destructive. The bananas obviously don't release their energy very fast. If it takes you 10 hours to digest 2 bananas and extract all of the chemical energy from them, that's a power level of about 20 watts. This particular battery pack is rated at a 10C discharge rate, which means it can be discharged at 10 times its current rating in milliamp hours. Or if we call it amp hours, at 16 amp hours, 10C means that I can draw out 160 amps from this battery continuously without damaging the battery pack. That's actually relatively low. Most LiPo battery packs are rated quite a bit higher than that. But for my applications, I don't need a real high discharge rate. And if you can find one of these battery packs with the lower rated discharge, they achieve that by reducing the size of the conductors inside and making it lighter. And so you can get a lighter weight battery pack with the same capacity if you're willing to live with a lower available discharge rate. Another really important thing about batteries is that they can be often the heaviest part of a quadcopter. And this is some footage from a drone that I built some time ago where I had the battery mounted not real high, but higher in the fuselage than I would have wanted. And I also had some camera equipment mounted above that. And so this drone had a relatively high center of gravity. and that's okay. The flight controller is able to keep it balanced for the most part. However, if you get the drone into an attitude where it's banked sharply, things start to get problematic. That high center of gravity starts to shift so far that the flight controller has an increasingly difficult time maintaining balance of the drone. The flight controls consist of the receiver with its simple antenna that came with my radio system connected to the flight controller board. And the flight controller board is the brains that runs the quadcopter. It contains a microprocessor, and it has sensors that can sense acceleration and can sense angular acceleration using solid-state gyroscopes. So its main job is to translate signals coming from the radio system from the stick inputs that act rather like rudder, elevator, ailerons, convert those into signals that drive the electronic speed controllers to run the motors, so that the quadcopter can be flown pretty easily. The flight controller can keep it level more or less by itself, and then you can give it conventional control inputs, and the flight controller manages the 4 motors appropriately. There are many types of flight controllers available at varying costs. This is a really simple one that I'm going to use. It's a CC3D. It's been around a long time. It doesn't have a lot of fancy bells and whistles, but it does the job. It's a really nice basic flight control. If you just want a model that flies, it's a good choice because there's not a lot of complexity. Here's the radio I'm going to use for this project. This one is a Fly Sky FST6. It's a very inexpensive radio system. You can certainly get better ones and much more expensive ones, but really a basic radio like this is fine for getting started. Well, that pretty much covers all the individual components and how they're specified. So in the final segment, I'll show you how we make specific design choices, how we choose the parameters of the components, the motors, the speed controllers, the battery, so that they all work together to give us good performance. So off we go. To calculate the expected performance of my drone, I use an quadcopter calculator that's available at ecalc.ch. You can use this service for free with a limited set of components, but to register is really inexpensive. You can get a month access to it for 99 cents. I went the whole way and spent about $6 for a year access to this, so it's pretty reasonable. So this is the first design I considered, and in this design I considered using a set of motors that I already had from a previous quadcopter. I won't go through every single parameter on this page, but I'll go through the most interesting ones. I entered a model weight of 500 grams without drive, which means without the battery, without the controller, the electronic speed controllers, motor and propeller. And doing it that way is kind of useful because if you swap in a different battery, it'll take the weight of that battery into account automatically. My frame size is 333 millimeters. The battery cell I plan to use is the 5200 milliamp hour 3S battery that I showed earlier in the video. Maximum discharge of 90% means I'm not going to discharge the battery 100% because that'll ruin it. You can take it down about 90%, so about 10% remaining without damage. Voltage per cell is a standard 3.7. The C rate on this battery pack is 10C, as I showed earlier, continuous, and this battery pack will allow a 20C maximum discharge rate for a short period of time, a burst. And this is really important here. You need to enter the weight of a single cell in the battery pack, not the entire battery pack. So this is a 3S pack, so I just weighted and I divided by 3 to enter the weight here. For the electronic speed controller, initially I considered using some that I had from a previous model that crashed. Those were 12 amp controllers, and I was going to use the motors from that model, which are made by Sunny Sky. This is the model number, and they're rated at 2300 kV. I mentioned the kV rating earlier in the video. And then finally for the propeller, on those motors I used a 6-inch diameter propeller with a 4-inch pitch, 2 blades. Those are the main parameters. And if you press calculate, software will determine predicted things like the load, how much power is used at peak temperature, and so on and so on. And the main one I'm interested in this case is hover flight time, and it predicts about 13 minutes. Here's my revised design. and I changed to a different motor. This is made by RC InPower. I chose that particular manufacturer, quite frankly, because they were on sale, and I got a good deal on the motors. But I went down to a 1900 kV motor instead of a 2300 kV motor. All the other parameters are the same, except I went up to 8-inch diameter propellers. I tried a number of different pitches, and the shallower the pitch for hovering performance, the better you're going to do. And so this is the shallowest pitch, the smallest pitch I could find in readily available propellers in this diameter. And so when I calculate expected performance of this, everything's the same except I changed the motors and went to a bigger propeller, but that's it. Now my flight time went from about 13 minutes before to 20 minutes in this design. So choosing the right motors can make a huge difference. And now I'll scroll down. What I'm really interested in is the flight time graph, which is this light colored sort of tan line here. And you can see it's based on flying speed. And so at flying speed of 0, I have my maximum flight time of a little over 20 minutes. And that's probably what I'm going to be doing most of the time. Well, I've shown you all of the components I'm going to use and showed you how I optimize the design to get the performance that I want. And so that's going to wrap up part 1 of this video series. In the next video series, part 2, I will take the basic quadcopter frame, I'll hook all the parts on it, connect them all together, set it up, and go flying.